Okay, this is lecture 15 on Quadrature Amplitude Modulation Transmission at the University of Texas at Austin for the class Real-Time Digital Signal Processing. So in previous lectures, we've talked about pulse amplitude modulation, transmission, and reception. Today we'll talk about quadrature amplitude modulation, and it's going to build upon what we've seen in pulse amplitude modulation. So in pulse amplitude modulation, so again, the definition of modulation, it just means that we're going to change a parameter. We're going to change some parameter of a known signal so that we can convey information. So for us, we're going to use that modulation to convey information. And for us, the carrier signal is generally if it's a bandpass transmission, our carrier is a cosine or sine. If it's and we also have a pulse shape involved. So there's two different ways that we can put information there. So for baseband PAM, we're going to modulate the amplitude of the pulse. The pulse could be raised cosine, square root raised cosine, rectangular pulse. And we're going to modulate, which is to change the amplitude of that pulse, which is the symbol amplitude we look up in the constellation map, to convey information. Right, so the normal procedure in PAM, consider just 2 PAM for an example. So for 2 PAM, I have a bit of value 1, bit of value 0. I map that to a 0 to a bit here, and then an amplitude. So I map a bit of value 0 to minus d, a bit of value 1 to plus d. And the value d and minus d are really used to scale the pulse shape that we're going to use for transmission. So we are changing the amplitude of a pulse shape to convey a message. And that message is a bit stream at the transmitter side. And it was up to the receiver to undo the operations to get back to an estimate of that bit stream. Okay. And PAM, may or may not be upconverted. So we've looked at baseband PAM, no upconversion. We've looked at that in Lab 5. We've looked at that in some of the homework problems. Not a problem. But the problem is, well, one issue of using baseband PAM is I need to have low frequencies available in my communication channel. Don't always have that luxury. So in many cases, for RF communications, for example, I'd have to upconvert the PAM for transmission. Then I would multiply by a cosine to shift the center frequency from 0 to a new carrier frequency. So PAM may or may not be upconverted. Either way has an important role to play. So an example of baseband PAM that's actually used in practice is, I've mentioned this before, which is the high-speed DSL standard version 2. And DSL is digital, it has different definitions: digital subscriber loop, digital subscriber line. I've seen different expansions of that acronym, version 2. So HDSL2 uses PAM, baseband PAM in transmission. So you'll see baseband PAM more often. This is a wired communication for business access to the internet. It's an older standard, a little more than 10 years old. All right, so we do use baseband PAM in practice, but we also use upconverted PAM as well. All right, now, where PAM plays is actually more used is actually not as PAM, but as QAM. So PAM is actually not all that common. PAM is also used in dial-up, the old dial-up modems over the phone line. They use PAM as well. Again, a wireline application. Now, where PAM plays the biggest role today is actually its role as part of quadrature amplitude modulation. So now for quadrature amplitude modulation, we're going to have a two-dimensional extension of PAM. So I'm going to have 2 PAM signals being transmitted together. We've looked at this already, but just to review here. So it's two-dimensional extension of digital PAM. So I have 2, at least at the transmitter side, independent PAM signals combined. Into one QAM signal. And to do this, we have to have sinusoidal amplitude modulation. We have to have upconversion for this to work. Now, the good news is the sinusoidal amplitude modulation that we use for the upconversion does not have to be at a very high frequency. It does not have to be at RF. It just has to be a high enough carrier frequency that I don't get aliasing or I don't get overlap at baseband between in my bandpass transmission. I really want bandpass transmission here. Now, later I can upconvert it again. So this is all done. So this first step is done typically digitally in this first step. So this is typically digitally for the baseband QAM, typically in digital. And discrete time for the baseband part. And then later, after it goes through a digital to analog converter, then we will probably upconvert it again for transmission. Or we might combine multiple baseband QAM signals at still in discrete time digital using a fast Fourier transform that gives us parallel streams, and then we convert that to analog using a digital analog converter. So the FFT based approach is what's common in Wi-Fi, asymmetric DSL or ADSL, VDSL, very high speed DSL, power line communications, cellular LTE. All these use the FFT based QAM approach. Okay, but in all those above, so for Wi-Fi, cellular LTE, we're going to later convert these QAM signals to some radio frequency for transmission. So 2 stages, baseband and then possibly an upconversion stage in continuous time analog circuits. All right, so back to baseband. So for digital QAM, we're going to modulate information onto pulses that are then subsequently modulated onto either amplitudes. You can think of this these are equivalent views of this. Either I have 2 PAM signals and one PAM signal is upconverted by a cosine, and the other PAM signal is upconverted by a sine, and then we subtract the 2 to get one signal. We've looked at this before in homework set 3. Or you can look at this, since I have a sine and cosine of the same frequency, I can do trig formulas to put that into one cosine with a phase and an amplitude function. And if I do that, I can represent the transmission as a single sinusoid where I put this digital information in both the amplitude and the phase. And both are very useful. Both views are very useful. The first view is really more how we're going to implement. Right? This is how we're going to actually build the transmitter. We're just going to build it out of PAM pieces that we already know about and add up conversion and a subtraction. So this is more the implementation side. Now we can also look at this from a theory side too, but this is more on the implementation side. Now the other approach, looking at amplitude and phase of a single sinusoid, this gives us more on some analysis. In particular at the receiver, because what this tells us, this second view tells us that both amplitude and phase are important. So it means that my receiver needs to get the amplitude correct, so my automatic gain control has to be right, my equalizer has to be good, and I also have to get the phase right. So my phase lock loop can't make too much error here. Like I had a lot of flexibility for upconverted PAM to have a phase lock loop that had error in it. It takes a lot of error to mess up PAM. 90 degrees will do it. So your phase lock loop has to make a lot of mistakes. It has to be way off to throw off PAM. But for QAM, we're going to see pretty quickly that no, the phase is you're very sensitive to phase. Your PL has to be much more precise in QAM. We'll see this in the constellations. So we're not going to use the second one very much, except to realize that phase is we're more sensitive to phase for our purposes in this class. In a digital communication theory course, you would probably go into more detail in the second view of it. Now there's a handout on modulation in the course reader. It's handout I, if I'm got that correct. And it looks at a bunch of modulation methods in this kind of unified framework of changing the amplitude and phase of a single sinusoid to carry a message information, or to carry information. And it puts a lot of modulation methods into the same framework. Amplitude modulation, even frequency modulation, phase modulation, and so forth. So take a look at the handout. Okay, so let's review. We've seen these slides. I think this is at least the fourth time in lecture, so this should definitely be, review on this one. But important to build the, again, to kind of build the implementation side of what we're doing, and also some theory here. And this relates also back to homework 6.3 that you did for Friday on QAM transmission. All right, so we're going to have two channels in QAM. We're going to have one channel of PAM that's upconverted and another channel of PAM that's upconverted. So the first channel of PAM is going to be upconverted according to the cosine. So this X1 is going to be a baseband signal. This is going to be, in practice, a baseband PAM for what we're going to do. So it's going to be pulse-shaped, and we'll have some amplitude scaling based on the bit pattern or bits we want to send. And we're going to modulate by cosine at low frequency. This is the first stage. This is the baseband QAM side. Now, the same analysis works if the cosine here is on a radio frequency carrier. This also works just as well. All right. But for now, let's assume X1 of t is an ideal low-pass signal. So this is our baseband PAM signal is bandwidth omega 1. Assume that again, this much less than is not so, less than is usually good enough here, but assume that the signal bandwidth is less than the carrier. This means that we don't get any overlap at the origin in the frequency domain at zero frequency. Assume that, if the Fourier transform of little x of 1, right, so big X of omega is the Fourier transform continuous time of x of t, so we assume it exists, and also that it's, just for the purpose of this discussion, that it's real valued. And what we've seen before is that if x1 is real valued, then after upconversion, y of t has a real value Fourier transform. So again, if x of 1 is real valued, band limited is all idealism, two-sided signals, all theory, there's no noise here, there's no any other mistake, it's just all pure idealisms here. But a good starting point. So if I do the upconversion, again I shift the baseband signal to the right by the carrier and left by the carrier, and the key is that I want to make sure that the carrier is high enough so that I have a gap between the bands, that I really have bandpass transmission. And so what do I need for that gap? What omega c has to be what? What's omega c have to be? Up here I say much greater than omega 1, but really well, there's no sampling here. It's all, this treatment's all continuous time, so we haven't gotten to sampling yet. But we would eventually, in an implementation for digital PAM, go to we need a sampling operation, or at least sampling to the point where we can do a digital analog conversion later. But we want this left edge to be in positive frequencies. We don't want it to spill over in the negative frequencies. So we really just need omega c greater than omega 1. That's all we really need. Now, in practice, we know that these pulse shapes, whatever we use, are not going to be ideally band limited. Of course, they are going to die. They're going to be some stop band, and so forth. So really, what this means is we want the stop band to be still in positive frequencies, so that the DC component is very little. In fact, generally, it's going to be 0. The average value here will be 0 if symbols are equally likely in our PAM constellation. Or QAM constellation, or QAM constellation. Okay, so in practice, we'll need omega c not just bigger than omega 1. We'll probably need it bigger than, say, 10% more than that, 1.1 times omega 1 in practice. Some time for the transition band. It's also possible that it also depends on the kind of pulse shape that we use. Well, that's actually, the pulse shape tells us what omega 1 is. And we need a little bit more room for the roll-off to stop band. Okay, so this is on the transmission side, and then on the, as we know from amplitude modulation by the cosine. The demod, or the demodulation, is simply modulate the low-pass filter. Now, this brings up some issues on the receiver side. The receiver needs to know what? What does the receiver need to know to do this properly? The phase of what? The cosine. So I need to know the cosine phase. Here I assume 0, but it's some constant. Or it might even vary a little bit with time. And what else do I need to know? I need the frequency. So the modulation, really in practice, I need to know the carrier frequency and the phase of this first upconverted signal. All right, we'll have a second channel in a second, in just next slide or so. And the low-pass filter has to know what? What does the low-pass filter need to know? Bandwidth of the original signal. So it needs to know, so the modulation needs to know omega c and theta 1, and the filter needs to know omega 1. Okay. Now omega 1 is going to relate back to the symbol rate. Right, omega 1 is a function of the symbol rate and the pulse shape that we use. Right, so if it's a raised cosine, so think about a raised cosine. So if the pulse shape, were a raised cosine, what's omega 1? Yeah, so we have a symbol rate in there. We originally called it capital W, where capital W was 1/2 the symbol rate. Right, that's the ideal. That's for the. It goes back to the two-sided sync. All right, what's in front of that? Now we're. Oh, there is a 2 pi in there. Absolutely, there is a 2 pi. And something else. There's no sampling. There's no sampling yet. There's no sampling. There's another parameter in the raised cosine. Alpha, right? The roll-off factor. So what's in that parenthesis? 1 something alpha. 1 plus. I'm feeling, yeah. All right. 1 plus alpha. And alpha is this roll-off factor that has value between 0 and 1 inclusive. When alpha is 0, we're back to the two-sided sync. Right, and when alpha is 1, we have full cosine roll-off. All right. All right, so that's the one channel. That's our first channel. So let's move on to the second channel. And of course, so back to the receiver, we're going to have to do carrier frequency estimation and correction and some sort of phase-lock loop. Let's do the second channel for QAM. So we'll have another channel that's PAM, a different PAM signal, so X2. This is the second baseband PAM signal. And it's going to be upconverted through sinusoidal amplitude modulation by a sine wave at carrier frequency omega c in radians per second and a 0 phase for the purpose of this slide. And again, we assume X of t is a baseband. Again, it's another baseband PAM signal. It's independent of the first one, also pulse-shaped and scaled by our symbol amplitude. And again, we don't really need this much greater than is a little overkill. Theoretically, we just need omega c greater than So in theory, we just need omega c greater than omega 2. You know, in practice, again, greater than maybe 1.1 times omega 2. Depends how you define bandwidth. If you define it as the passband, then it'd be 1.1 times omega 2. Now, if if our spectrum here, our Fourier transform of the baseband PAM signal were real valued, then the Fourier transform of the after upconversion is imaginary value. And I draw again the imaginary amplitudes here as a dotted line. But independent of that, or separate from that, the content in the frequency domain shifts to the right by the carrier and shifts to the left by the carrier. Seen that many times before. You see that mathematically. So that means that part, omega minus omega c, means shift to the right, and omega plus omega c is shift to the left. And we still scale by a half. That hasn't changed. What has changed is we get the scaling by j, minus j and j. So now suddenly we have imaginary valued amplitudes in the Fourier domain. We still want a gap. We still would like a gap here between our bands. Now, demodulation follows the same approach. We're to modulate in the low-pass filter, and again, we're still, now I need to find omega c again, but I've done that already to support the first channel, and I need to find the phase. And we really, now, how do you relate the phase here on the second channel to the first channel? What's the phase difference? 90 degrees. So we want to keep the phase difference between the sine, whatever signal we're using here for the sine wave, to be 90 degrees out of phase of whatever we're using for the cosine. We'll talk about that in the block diagram coming up. Now, on the transmitter side, it's easy enough to do this. This is lab 2, generating cosines and sines. We can be pretty accurate on the transmitter side to keep these 90 degrees out of phase. Look up tables, difference equations, whatever we want to do to implement the cosine and sine. But now on the receiver side, we want to do our phase lock loop so that we keep these 90 degrees out of phase. And a low-pass filter is the same. So again, this low-pass filter, you know, really is what? What's the impulse response of this low-pass filter in practice? Well, we already know it's tuned. We know from the previous slide it's tuned to the pulse shape, or something about the symbol rate. But again, we got 3 filters. It turns out we have at least 2 filters here in the receive side. We've got the modulation low-pass filter, and we have a match filter, which is also low-pass. So why have 2 low-pass filters when one will do just fine? Right. So typically we'll replace the cascade of this modulating, or demodulating, if you want to call it that, a demodulating low-pass filter, cascaded with the match filter. We'll just use a match filter. Go ahead.
Does having 2 filters
No, they're FIR. These will be FIR. Now you're right. So this filter here doesn't have to be. This could be either IIR or FIR. That is correct. But for the pulse shaping for the match filter, we know it's finite impulse response, simply because our pulse shapes are finite in duration. So this could be either IIR or FIR. So if we go, but again, we can just, for simplicity, replace it with the match filter. Remember, we still have an equalizer in the system. The equalizer will clean up a lot of mess. That's coming up in Friday's discussion. Still in two lectures from now. All right. Now we can put this together into one block diagram. I think that's it on the, yeah. Sorry. All right, so for putting this together, this is our QAM transmitter, done in a mixture of continuous time and discrete time, mostly continuous time, and we'll make it discrete time in 15-9, slide 15-9. Okay, so what do we do here? So here's the part that we already looked at many times before. That's baseband PAM, right? We take an amplitude, here I sub n, for the in-phase component, and this is a symbol amplitude from a constellation map. plus d minus d, so forth, plus 3d, whatever it happens to be. We scale, we send that in to scale the areas under an impulse modulator. We then pulse shape the output of the impulse modulator. The impulse modulator gives us an impulse that's separated by what time? What's the separation in the impulses in the impulse modulator? Symbol something. Let me help you. Symbol time. There you go. Very good. Run the time domain. That's correct. That's correct. All right. So the areas here would be, I0, I1, I2, and so forth. And then we're going to pulse shape this to limit the bandwidth, right? The impulse train has infinite bandwidth. All right. So we've talked about this already. And then we're going to upconvert this with a cosine. So this is basically our cosine. Cosine modulation. All right. The second channel of QAM, well, I'm also going to have another baseband PAM step. Impulse modulation followed by pulse shaping. I have another constellation map set, for PAM. It's a separate PAM signal, if you will. And then I'm going to upconvert with the sine. So here's sine modulation. And I just have to make sure that these two are 90 degrees out of phase. Now, in discrete time, this is pretty easy to do because we can generate cosines and sines separately very easily. We did this in Lab 2. It was a different, we also Lecture 1, difference equation, lookup table, math library call. Pretty easy to generate cosine and sine separately and keep them 90 degrees out of phase. We don't have to have a single oscillating source and then split that into two signals, cosine and sine. In some cases, this is what we have for, it's a lower cost oscillator. So remember this part of the block diagram, the local oscillator is shown as in continuous time in analog domain. So we could have a very inexpensive analog local oscillator, and we have to split that one reference signal into two oscillating signals that are 90 degrees out of phase. And there's a way to do that by having a 90 degree phase shifter, which it turns out to be an FIR filter, and a matched delay that matches the group delay through the FIR filter that does a 90 degrees phase shift, and you can generate two signals that are 90 degrees out of phase. And we'll talk about that in the next couple of slides. But that's in continuous time. But in discrete time digital, why go through that? We know how to do it directly. Lookup table. In fact, we just do one lookup table, which is the cosine. And for the sine, how would you index into a cosine lookup table to get the sine? That's a really short lookup table. Okay, that's a little bit more. Okay, so you're on the right track though. If the cosine looks something like this, right, and the sine wave looks something like this, that is way too wide for a sine wave, so we're just going to try that again. Okay, we're going to get this right. Oh boy, I'm having a special day here. All right. Draw the sign first.
It's going to be
0. So there's a 90 degrees phase shift, which corresponds to a time delay, right? Time delay is 1, so you're on the right track. It's quarter of the period. So if I have the cosine in memory as a lookup table, then I can get the same value simply by the right phase shift or the right delay into the entry. So if I look at what happens on the blue curve versus the red, so if I match Right, so I can do the right phase shift and get the right curve into this. Okay. Now, what would make it a little more complicated is this, these are 90 degrees out of phase, and then I subtract them. So sometimes we'll actually put the minus sign in the sine term. Here we don't. We just generate the sine and we negate later. But you can index into the lookup table with the correct offset. So if this entries were, if I had 400 entries, then it would be the right quarter length, quarter of the period to index them in the same table. So here I get the same values in red as I get in blue. All right. So one lookup table is enough, but I can also generate two lookup tables if I wanted to, use the memory. Okay, so that's all the continuous time side on the right. On the left, it looks a lot like PAM, but there's a slight difference in that I still have a stream of bits that are coming at me, and I group them into capital J bits per symbol. That doesn't change. But now I have a constellation map that's two-dimensional because I want to generate the symbol amplitude in the in-phase direction and the symbol amplitude in the quadrature direction. So I have the in-phase component, and I have the quadrature component. But if you look at this 2D constellation map, along the in-phase component, I have, along this direction, I have 2 PAM. And along the vertical direction, I also have 2 PAM. And the constellation spacing is still 2 times little d. So again, the in-phase direction, my possible values for I, capital I, are plus d and minus d. Along the quadrature direction, so this is little I of n. Along the quadrature direction, my possible values, again, are plus d and minus d. So I have 2 PAM in one direction, 2 PAM in the other, and the total possible combinations of the cross product. It's all the possible combinations, so I have 4, 2 times 2. But as a two-dimensional constellation, I have now, in the two-dimensional plane, my points are, for example, this one, that is plus d in the in-phase direction, and minus d in the quadrature direction. So I can write this as a complex number, which we do. So I can write this as, mathematically, as if I want to combine I and J, I and Q, I can think about back to the Fourier transform that in the Fourier domain, the in-phase upconverted signal was real valued, and the upconverted quadrature signal was imaginary valued. And if I add or subtract them, they don't interfere with each other. They're 90 degrees out of phase. Another way to represent that is as a complex value. So a representation here is really, you thinking of it as the in-phase component here is the real value, and the quadrature component here is the imaginary value. So we use this for mathematical purposes. We don't implement, or we don't transmit complex valued signals. Right, we have to do real valued signals over our media. But mathematically, we can think of this, since they're 90 degrees out of phase, using a Cartesian but complex representation, complex valued representation. Okay, so the first part of this should look, the first 2 blocks look very familiar. Standard stuff, even for PAM. But the difference here is that my constellation map is two-dimensional. The 2 channels of PAM look familiar. The upconversion looks familiar. We're just combining them here to get one transmitted signal S of t. And that transmitted signal is a baseband signal, and it contains both PAM signals. Okay, so one of the cool things here is that I'm getting 2 PAM signals in the same transmission bandwidth as I would have gotten 1 PAM signal. Remember, there's a efficiency factor that we lose if we just did upconverted PAM. I end up doubling the bandwidth of the message signal when I upconvert. Seems wasteful. So the good news, again, we saw this back in homework 3, the good news here is that I can put a second PAM signal into the same transmission bandwidth without, at least on the transmitter side, the two interfering with each other. As long as I can keep the two modulation signals 90 degrees out of phase, then I keep them separated and independent of each other. Now, once it goes through a channel, there's a little bit of cross-contamination or leakage, and you saw that in homework 3. You quantified that in homework 3. Okay. But now, again, if we now look at this constellation map, we'll see that the phase now starts to matter more. I need a better, for here, the phase error still can be maybe 45 degrees, and I'm doing a pretty good job, and 90 would get me in trouble pretty fast. 90. So if I think about phase error, just rotate the constellation by that phase error. So if I make 90 degrees phase error, it's like rotating this thing 90 degrees. Everything's wrong. Right? All the symbols are in error. Now, if I rotate by 45, I might be okay. I'm on these threshold boundaries for detection. If I rotate by, say, 20 degrees, I'm probably pretty okay. Okay, so PAM, this is 4QAM. The higher the constellation, the more sensitivity I have to phase. So phase now becomes more and more significant to worry about in the receiver. So let's talk a little bit about the phase shifting, and then we'll make this discrete time before we break for today. All right, so a few words on this phase shifting. Any questions on this? This is pretty important. This is lab 6. Almost lab 6. We'll make it discrete time to make it lab 6. This is the basis for lab 6. All right, so let's talk about a phase shift. And this is kind of interesting to do this phase shift. Lots of ways you can do the phase shift. But if we want to come up with a block that will take any sinusoidal signal in and shift it by 90 degrees in phase, regardless of the frequency, as long as the frequency isn't 0, then this is one way to do it. If we just want a flexible block for lots of different frequencies. So this phase shift, this more flexible, phase shift by 90 degrees is one way to do this is called a Hilbert transformer. In the end, it's an FIR filter. And you can design it using Parks-McClellan if it's discrete time. So what we want to do is do the following. If a cosine comes in, we want a sine to come out. If a sine comes in, we want a minus cosine to come out. So look at the Fourier transforms of this. Here's the Fourier transform of the cosine, continuous time Fourier transform. Right, we get two direct deltas, one at f naught, one at minus f naught. Areas are a half. If we put in a sine wave, so what's a Fourier transform of a sine wave? It's the same direct deltas, at least in location, but you'll notice that the amplitudes are slightly different. We have j over 2 instead of 1/2, and here we have minus j over 2 instead of 1/2. So we want to start thinking about this as a linear time invariant system with a magnitude and phase response, or more generally a frequency response. So we're going to have to have 0 initial conditions and so forth for LTI properties. So here's our frequency response. What we like to say is that if a frequency comes in, really we don't want to change the magnitude here, we just want to change the phase. Okay, so if we look at the magnitude response, it's going to be 1, although DC causes some trouble, so DC doesn't work for us here at all. We need to have some frequency that's not 0 in the sine and cosine. Hard to phase shift DC. All right. So the phase response here, if I want to convert so if I want to feed a cosine in, then what I'd like to do is, so another way to look at the scaling here from cosine to sine, so if a cosine comes in, we want a sine to come out, then for negative frequencies, we want to scale by j. For positive frequencies, we want to scale by minus j. So that gives us some insight on the frequency response we'd like to have. Right? So for the frequency response we'd like to have, for negative frequencies, multiplying by j is the same as 90 degrees, right? So J can be written as, right, e to the j pi over 2, right? So that's a 90 degrees phase shift. So that's this one, pi over 2 phase shift. And then minus j e to the minus j pi over 2, right, going the other direction. And so that phase shift, and again, in degrees, pi over 2 is 90 degrees, and minus pi over 2 is a minus 90. And so that's this term. Now you can see at DC we have some trouble. If I have zero frequency, then my cosine term is what? What value is that? I have cosine 2 pi f naught. F naught is 0. It's 1. And for the sine, f naught, so 2 pi f naught t, and f naught is 0. 0. So I have to turn a 1 into a 0 and a 0 into a minus 1 on this one. I don't know how to do that. Okay, so we DC is just forbidden, basically. We just don't allow it through. So there's a notch at DC. Or you can design it and just assume that the designer is never going to give us a DC signal. So let the designer put the notch at DC in before the phase shift. However you want to do it. All right, so this is the magnitude and phase responses, and so it's an all-pass filter except at DC, possibly, and the phase shift is either plus 90 degrees or minus 90. Now, what's your guess at the impulse response here in terms of symmetry? Any symmetry you think is here? Any symmetry in the phase?
Yeah.
What's the symmetry in the phase? Odd symmetry? What's your guess on the... Correct. I'll have odd symmetry in the impulse response.
About the center of the impulse.
Correct. At the center of the impulse response. That's right. About the midpoint, if you will. Right. Okay. So we're not going to derive this Fourier transform relationship. This is something you might do in another class. DSP theory, you might do it, for example, on the discrete time ideal Hilbert transform. We're just going to use, this is from a lookup table. So if we look at the inverse Fourier transform, so we know that this is our target frequency response from the previous slide. The impulse response is pretty strange. Now, it is odd symmetric about the midpoint. The midpoint's a bit odd because it's on, we just let it be 0. Otherwise, in the limit, from the left it goes to infinity, and from the right it goes to minus infinity, so we'll just call it 0. And then in discrete time it looks something like that too. So in discrete time we want this Fourier transform. Either get a plus or minus 90 degrees phase shift, all pass otherwise. We might exclude DC. The impulse response for that transfer, for that frequency response, is as follows. It has the same kind of form as a 1 over time in the impulse response, but a slightly different numerator. But if you look at if we just kind of connect the dots, so here the stem plot here would be the actual samples. Every other sample is 0, which is kind of a little odd. And if you look at the envelope, in positive values of n, it looks like 1 over n, or it's proportional to 1 over n. And in the negative values of time index, we see the same kind of relationship as we saw in the continuous time impulse response. So here we have is a, it's a linear phase. Certainly has the right properties of linear phase. Since the midpoint's at 0, in this case, we can get we get a 0 phase is one way it could happen if this were even symmetric. Odd symmetric, we get the phase response you saw on the earlier slide, plus or minus 90 degrees. Now this is not implementable because this goes for all time. Right, so to implement this, what would you do? Window it, and then what? Well, that's already sampled. The one on the right. Well, it's not downsample yet, but let's just make this something that we can put into an FIR filter block. Okay, we can throw away the zeros at a later time, because this happens with interpolating filters and so forth anyway. But what we do with the raised cosine, or the sink that was two-sided, what did we do to make it implementable as a pulse shaping filter? We shifted it, but before we shifted it, we windowed it, is what you said. So we're going to truncate. So truncate some, 2, 3, okay. Truncate and then delay to make it causal. And the delay will cause, the phase now will be linear phase because of the delay. Right. Okay, that's what we'll do in practice. Now, in practice, so we keep an odd number of samples in the impulse response. So we can represent the odd number. So we approximate by an odd length linear phase FIR filter. We truncate the response to be 2 L plus 1 samples. We take L samples left of the origin, L samples right of the origin, and the origin itself. We then shift the impulse response by L samples to the right to make it causal. And if you look at this, L is going to be odd because every other sample in the impulse response is 0. If L is even, we're just picking up 2 more zeros. What's the group delay through the filter? Right, the group, because we have the symmetry, it's going to be odd symmetric about the midpoint. So the group delay is a linear phase FIR filter of length n, has the same phase response as an ideal delay of length quantity n minus 1 over 2. That means that the group delay is L. It's always integer, which is nice. So the match delay on that block diagram is a delay of L samples. In other words, it takes L samples for this FIR filter to give you the 9 degrees phase shift. You have to match the delay in the upper part of the block diagram so that when comparing the cosine signal and the sine signal that you're generating from the one oscillator, they will be 9 degrees out of phase. And I will tell you in books, they often forget the match delay block, assuming I think you know to put it in. But it needs to be there for this to work. All right. So let's end, and we'll come back to this on the next lecture, but this is the conversion from the QAM transmitter earlier on slide 15-15, sorry, 15-5, put completely into discrete time. So we go through the same process as we did with converting PAM from this mixture of discrete and continuous time to solely discrete time. Replace the impulse modulator with upsample by L, where L is the number of samples per symbol, also the upsampling factor. And we we also sample the cosine and sine, but we know exactly how to generate those separately. Lookup table, difference equation. We still subtract the upper and lower bandpass PAM signals, upconverted PAM signals, and we push this through a digital analog converter to get our continuous time analog signal out that corresponds to baseband QAM transmission. And this is, the bottom part is lab 6. Just builds on what you've done on all the previous labs. So this would be lab 5. The cosine and sine is lab 2. Pulse shaping filter is lab 3. You know there's PN in here somewhere. We'll get to that, but it's for training signals from lab 4. All right, but this block diagram is really labs 2, 3, and 5 put into all kind of combined. And the appropriate homework problems as well in each of these blocks. Okay, we'll pick this up on next time.